Today we are going to discuss molecular orbital theory. This is the most advanced theory and it was developed by Robert S. Mulliken. This theory was based on the dual nature of electron. That means electron can behave as a particle as well as a wave. Molecular orbital theory suggests that all atomic orbitals of different atoms come together and they produce molecular orbitals. Thus, all atoms participate in bonding to form a molecule. These molecular orbitals are associated with all nuclei in the molecule. If it doesn't make any sense to you, just wait and have patience. You will understand everything about molecular orbital theory. But how these atomic orbitals combine to form molecular orbitals? First of all, atoms come to a equilibrium distance. For example, this is atom A and this is atom B. These are the atomic orbitals. So these atomic orbitals come to a equilibrium distance and after that they produce molecular orbitals. So this is the molecular orbital of molecule AB and this is the another molecular orbital of molecule AB. When two atomic orbitals combine, they produce two molecular orbitals. This approach is called as linear combination of atomic orbital, or the short form is LCAO. So let's try to understand LCAO in detail. When two atomic orbitals overlap, there will be two possibilities. Either they are facing similar sign or they are facing opposite sign. So what is the meaning of signs here? If you remember, molecular orbital theory is based on the dual nature of electron. And what is an orbital? Orbital is the place where the probability of finding an electron is maximum. That means it is a place of electron. If electron has the dual nature, orbital will also have a dual nature. If we consider electron as a wave, orbital can also be represented by a wave function. So this is a wave. And this is the line of propagation. Above the line of propagation, it is represented by a positive sign, and below the line of propagation, the part of wave is represented as minus sign. That's why every orbital carries positive and negative sign. So in first case, either they're facing similar sign, and the other possibility is that they are facing opposite sign to each other. So let's see what will happen if they are facing similar sign. For example, this is atom A and this is atom B, and these are the atomic orbitals. They both are facing similar signs to each other. As we just have discussed, orbital can also be expressed as a wave function. So if I consider psi AO is a wave function for atom A and psi dash AO as a wave function of atomic orbital of atom B. If you observe both the waves, they both are in the same phase because they both are identical to each other. If both the waves are in same phase, their wave functions add to get more enhanced wave function. So when you add both the wave functions, you will get more enhanced wave function, and this is the wave function of molecular orbital of molecule AB. It results by the addition of both the wave functions. Because of it, electron density increases in between the nuclei, that in turn lead to a stronger bonding of orbital. And the molecular orbital result by the combination of both atomic orbitals is known as bonding molecular orbital. Now consider the another possibility if atomic orbitals facing opposite signs to each other. So here this is atom A and this is atom B, and they both are facing opposite sign to each other. So first draw the wave function for both the orbitals. This is the wave function of atom A and psi dash AO is the wave function of atom B. Here if you see, both the waves are in different phase. When you add both the waves, wave functions get cancelled by each other and you will get a smaller wave function as a result of destructive interference. This is the wave function of molecule AB. Due to destructive interference, electron density decreases to zero between the two nuclei, and it results in the formation of antibonding molecular orbital. So far we have discussed how bonding and anti-bonding molecular orbitals are formed by the combination of two atomic orbitals. That's why when two atoms A and B combine together, they result in the formation of two molecular orbitals. One is bonding and other one is anti-bonding. That's how two molecular orbitals are formed by the combination of two atomic orbitals. Now discuss which two atomic orbitals can combine to form a molecular orbital. Atomic orbitals of comparable energies and of same symmetry can overlap along the molecular axis. For example, s orbital can overlap with s orbital because they both have same symmetry. And what about the energy? 1s can only overlap with 1s. 1s cannot mix with 2s. Now come to the next rule. They result either sigma molecular orbital or pi molecular orbital depending on the symmetry of combining atomic orbitals. That means when s orbital overlap with the s orbital, they overlap along the intermolecular axis. That's why they result in the formation of sigma molecular orbital. For example, if py overlap with py, they overlap perpendicular to the intermolecular axis. That's why they result in the formation of pi molecular orbital. Each of them produces the set of bonding and non-bonding molecular orbital. As we just have discussed, if both are facing similar sign, they result bonding molecular orbital. If they both facing opposite sign, they result in anti-bonding molecular orbital. So every time, whenever atomic orbitals overlap, they produce molecular orbital. One is bonding and another one is anti-bonding. So let's see what happens when s orbital overlap with each other. As we just have discussed, there will be two possibilities. Either they are facing similar sign or they are facing opposite sign. There will be head-on overlapping between two s orbitals. Because of head-on overlapping, they result in sigma molecular orbital. If they are facing similar sign to each other, they result in the formation of bonding molecular orbital. This bonding molecular orbital is named as sigma molecular orbital. If they are facing opposite signs to each other, they result in the formation of anti-bonding molecular orbital, where there will be zero electron density present between the two nuclei. And this molecular orbital is named as sigma star. Here sigma star is used to represent the antibonding molecular orbital. This is the general convention to represent an antibonding molecular orbital by using star over it. So what is the energy order for sigma bonding and sigma antibonding molecular orbital? Bonding molecular orbitals are more stable than the atomic orbitals. Here you can compare the energy of atomic orbitals and molecular orbital. So this is the energy of atomic orbital, and here you can see this bonding molecular orbital has lower energy than that of atomic orbital. That means this molecular orbital is stabilized by the loss of some amount of energy. But when you compare the energy of antibonding molecular orbital, its energy is higher than that of atomic orbitals. That's why it is destabilized by some amount of energy. These antibonding molecular orbitals are in much stress because there is lack of compatibility between two atomic orbitals. Let's discuss how many molecular orbitals can be produced by the mixing of p atomic orbitals. We all know p subshell has three orbitals. One is px, another one is py, and third one is pz. When px orbitals overlap, they overlap head-on like this and result in the formation of sigma bonding and sigma antibonding molecular orbitals. This is the py atomic orbital of one atom. This is the py atomic orbital of another atom. They overlap sidewise. That's why they result in the formation of pi and pi star molecular orbitals. Similarly, pz atomic orbital, when they overlap with each other, they also result in the formation of pi bonding and pi anti-bonding molecular orbital. We are going to discuss each of them separately. When px orbitals overlap with each other, they overlap along the intermolecular axis, that means by head-on overlapping. When they are facing similar sign to each other, they result in the formation of bonding molecular orbital. And this orbital is named as sigma molecular orbital. If they are facing opposite sign to each other, they result in the formation of anti-bonding molecular orbital, and there will be no electron density present between two nuclei. And this is the nodal plane. Nodal plane is the plane where there is zero electron density. And this molecular orbital is known as sigma star molecular orbital. Now come to the py atomic orbital. When they overlap sidewise and they result in the formation of pi molecular orbital. If they both are facing similar sign to each other, they result in the formation of bonding molecular orbital. And if they are facing opposite sign to each other, they result in the formation of anti-bonding molecular orbital. Now come to the salient features of molecular orbital theory. Combining atomic orbitals must have comparable energy. As I just have discussed, 1s can overlap with 1s only. 1s cannot overlap with 2s. Combining atomic orbitals must have same symmetry along the molecular axis. That means, for example, this is py atomic orbital and this is pz atomic orbital. They both have same shape, but they both have different orientation along the intermolecular axis, so they cannot overlap with each other. Py can overlap with py only and pz can overlap with pz only. Combining atomic orbitals must overlap to a maximum extent. Greater the overlap, greater is the electron density between the nuclei, so the stronger bond form. Electrons in atomic orbitals are in influence of only one nucleus, but in molecular orbital they are under the influence of two or more nucleus. For example, this is atom A and this is atom B. This is the atomic orbital of atom A and this is the atomic orbital of atom B. When they both combine together, they result in the formation of two molecular orbitals. One is bonding and another one is anti-bonding. And these molecular orbitals belong to molecule AB. Electrons present in this atomic orbital is under influence of atom A. And electrons present in this atomic orbital is under influence of atom B. But electrons present in these molecular orbitals are under the influence of A as well as B. Atomic orbitals are monocentric while molecular orbitals are polycentric. As I just have explained, electrons in atomic orbital is under the influence of A, and here electrons present in this atomic orbital is only under the influence of B. But here this electron is under the influence of A as well as B. That's why it is a polycentric molecular orbital while atomic orbitals are monocentric. Number of molecular orbitals are formed is equal to the number of combining atomic orbitals. Here, two molecular orbitals are formed by the combination of 1 plus 1 atomic orbitals. When two atomic orbitals are combined, two molecular orbitals are formed. One is called bonding molecular orbital and other is known as anti-bonding molecular orbital. Now, how do you distribute electrons in molecular orbitals? Distribution of electrons in molecular orbital is also follow the same rule as does in the atomic orbitals. That means each molecular orbital can accommodate maximum 2 electrons like atomic orbitals. It also follows Aufbau principle and Hund's rule of maximum multiplicity. That means electrons are filled in increasing order of their energies in molecular orbitals. So let's discuss the formation of H2 molecule according to molecular orbital theory. So here it represents the atomic orbital of atomic hydrogen and this represents the atomic orbital of another atomic hydrogen, and at the center these are the molecular orbitals of H2 molecule. As we just have discussed, S orbital can overlap with S orbital they overlap head-on. That means they result in the formation of sigma molecular orbital. And as there are two possibilities, if they are facing similar sign, they result in the formation of sigma bonding molecular orbital. If they are facing opposite sign to each other, they result in the formation of sigma anti-bonding molecular orbital. That's why you will get sigma 1s bonding molecular orbital and sigma star 1s anti-bonding molecular orbital. So let's see how do we fill electrons in these molecular orbitals. First of all, you have to calculate total number of electrons present in H2 molecule. So there is one electron in one hydrogen and one electron in another hydrogen. That means there will be total 2 electrons in H2 molecule. Now fill the electrons according to Aufbau principle. That means first of all you have to fill electrons in lower energy molecular orbital. Sigma bonding molecular orbital has the lowest energy as compared to sigma anti-bonding molecular orbital. So that's why we are going to fill 2 electrons in sigma 1s molecular orbital. Now write the electronic configuration for H2 molecule. For writing of electronic configuration, you have to write it sigma 1s2 because we have filled 2 electrons in sigma 1s molecular orbital. But what is the significance of this molecular orbital diagram? Which information we can draw from the molecular orbital configuration or the molecular orbital diagram? First of all, you can calculate the bond order of the molecule. You can also predict the stability of the molecule. And you can also predict the magnetic behavior of the molecule. For the bond order calculation, you have to use the formula bond order is equal to Nb minus Na over 2. Nb is the number of electrons present in bonding molecular orbital and Na is the number of electrons present in anti-bonding molecular orbital. On the basis of bond order, you can predict the stability of the molecule. If you will get positive bond order, that means molecule will be stable. But if you will get negative bond order, that means molecule will be unstable. And if you will get zero bond order, that means molecule does not exist. On the basis of molecular orbital diagram and molecular orbital configuration, you can predict the magnetic behavior. If all the electrons are paired, that means molecule will be diamagnetic. But if is there any unpaired electron, molecule will be paramagnetic. Let's try to calculate bond order for H2 molecule. We have the formula Nb minus Na over 2, where Nb is the number of electrons present in bonding molecular orbital and Na is the number of electrons present in anti-bonding molecular orbital. So this is the bonding molecular orbital and this is the anti-bonding molecular orbital. In bonding molecular orbital, there are 2 electrons. So you will get 2 minus, there is none electron present in anti-bonding molecular orbital. So here you will write 0 over 2. So here you will get 1. That means bond order is 1. It represents the single bond. That means when the hydrogen molecule is formed, it is formed by the formation of single bond between 2 atoms. As the bond order is positive, that means this molecule will be stable. Now come to the magnetic behavior. If all the electrons are paired, that means this H2 molecule is diamagnetic in nature. Now come to the formation of Li2 molecule. And let's predict the stability of Li2 molecule. First of all, write down the electronic configuration for lithium. Its atomic number is 3. So the configuration will be 1s2, 2s1. On this side, this is the electronic configuration of one lithium atom, and on the another side, this is the electronic configuration of another lithium atom. And at the center, these are the molecular orbitals of Li2 molecule. When 1s overlap with 1s, it results in the formation of sigma bonding molecular orbital and sigma anti-bonding molecular orbital. Similarly, 2s will overlap with 2s and it results in the formation of sigma 2s bonding molecular orbital and sigma star 2s anti-bonding molecular orbital. Now fill the electrons in these molecular orbitals. First of all, you have to calculate the total number of electrons in Li2 molecule. In one lithium, there is 3 electrons. So in 2 lithium, there will be 6 electrons. So you have to fill these 6 electrons in these molecular orbitals according to Aufbau principle. So first of all, we will fill 2 electrons in sigma 1s molecular orbital. Now 2 electrons will be filled in sigma antibonding 1s molecular orbital. Now 2 electrons are still remaining. So these 2 will be filled in sigma 2s molecular orbital. Now write the electronic configuration for Li2 molecule. So you will get sigma 1s2, sigma star 1s2 and sigma 2s2. Now calculate the bond order for Li2 molecule. We have the formula Nb minus Na over 2. First calculate the electrons present in bonding molecular orbital. So there are 2 electrons in sigma 1s bonding molecular orbital and 2 electrons in sigma 2s bonding molecular orbital. So you will get 4 electrons present in bonding molecular orbitals minus how many electrons present in antibonding? There are 2 electrons present in sigma star molecular orbital, that is antibonding molecular orbital. So you will write 2 here divided by 2. When you calculate it, you will get bond order 1. There is single bond present between 2 lithium atoms. As the bond order is positive, this molecule will be stable and it does exist. Now come to the magnetic property. As all the electrons are paired, that's why molecule will be diamagnetic. Now come to the another example of N2 molecule. Here you will get a huge molecular orbital diagram, but don't afraid of it. First of all, write the configuration of nitrogen atom. You will get 1s2, 2s2, 2p3 as the atomic number of nitrogen is 7. Similarly, on the another side also you have to write the electronic configuration of atomic nitrogen. And at the center, these are the molecular orbitals of N2 molecule. When 1s overlap with 1s, it results in the formation of sigma 1s bonding and sigma star 1s antibonding. Similarly, when 2s overlap with 2s, it results in the formation of sigma 2s bonding and sigma star 2s antibonding molecular orbital. Here, these are px, py and pz. When px overlap, it results in the formation of sigma molecular orbital. When py overlap with py, it results in the formation of pi molecular orbitals. Similarly, pz overlap and result in the formation of pi molecular orbital. So here you can see this is pi 2py and pi 2pz. They both have similar energy. That's why I have written both of them at the same level. After that, there will be sigma 2px. It has some higher energy than that of pi bonding molecular orbitals. And pi antibonding molecular orbital have much higher energy. And after that, there will be sigma antibonding px molecular orbital. Now you have to remember the sequence of energy order of these molecular orbitals. Now we have to fill electrons in these molecular orbitals. In one nitrogen, there are 7 electrons. So there will be total 14 electrons in N2 molecule, and we have to fill 14 electrons in these molecular orbitals. So first of all, we will fill 2 electrons in sigma 1s bonding molecular orbital. Then 2 electrons will be filled in sigma antibonding molecular orbital. Then next 2 electrons will be filled in sigma 2s bonding molecular orbital. Next 2 electrons will be filled in sigma antibonding 2s molecular orbital. Now we have to fill electrons in these pi molecular orbitals. And they both are at the same energy level. So you have to follow Hund's rule of maximum multiplicity. According to this rule, First of all, you have to fill one electron in each molecular orbital. And after that, we can pair them up. Next electron will be filled in pi 2p y molecular orbital, and another electron will be filled in pi 2p z molecular orbital. Now calculate how many electrons we have filled so far. So 2 plus 2 4 plus 2 6 plus 2 8 and plus 4 12 electrons we have filled in. Now remaining 2 electrons will be filled in sigma 2p x molecular orbital. Now write the electronic configuration for N2 molecule. So you will get sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then pi 2py2 equal to pi 2pz2 as they both have similar energy. Then sigma 2px2. So this is the electronic configuration of molecular nitrogen. Now calculate the bond order. We have the formula Nb minus Na over 2. First of all, calculate the number of electrons present in bonding molecular orbital. 2 electrons in sigma 1s, 2 electrons in sigma 2s, 2 electrons in pi 2py, and 2 electrons in pi 2pz, and 2 electrons in sigma 2p x bonding molecular orbital. So that means there are 10 electrons in bonding molecular orbital and remaining 4 will be in anti-bonding molecular orbital divided by 2. So when you calculate it, you will get 6 over 2. Bond order is positive. That means molecule will be stable. And 3 bond order represents the triple bond between the two atoms. So there is triple bond between two nitrogen atoms. Now come to the magnetic behavior. As you see, all the electrons are paired. That's why N2 molecule is diamagnetic in nature. If you want to study the formation of O2 molecule according to molecular orbital theory, you have to remember one thing. Molecular orbitals doesn't follow the same energy order like atomic orbitals for all the molecules. It has different energy order for lighter molecule and for heavier molecule. Lighter molecules means in which total electron count is less than or equal to 14. For example, C2 molecule. In C2 molecule, total electrons are 6 plus 6 means 12 and it is less than 14. That means it is considered as a lighter molecule. Similarly, N2 molecule, it has total 7 plus 7 that means 14 electron that is equal to 14. So they both considered as a lighter molecule. And for lighter molecule, you can follow the same energy order as we have followed for N2 molecule. But if you want to try to write the molecular orbital diagram for O2 molecule, it doesn't follow the same energy order because in O2 molecule, total electron count is 8 plus 8 is equal to 16 and it is more than 14 electron count. So it is considered as a heavier molecule. And for heavier molecule, there is change in energy order of molecular orbitals. There is only a little bit change. Sigma 2px has lower energy that of pi 2py and pi 2pz. So this is the only difference between the molecular orbital diagram of lighter or heavier molecules. Now this molecular orbital diagram can be used for the heavier molecule like O2. So let's discuss the formation of O2 molecule. In O2, these are the atomic orbitals. Atomic number of oxygen is 8. So the configuration will be 1s2, 2s2, 2p4. And on the other side also, this is the electronic configuration of atomic oxygen. First calculate the total number of electrons in O2 molecule. So there will be 8 plus 8 is equal to 16 electrons. Now you have to fill these 16 electrons in these molecular orbitals according to O2 principle. So 2 electrons will be filled in sigma 1s molecular orbital. Next 2 electrons will be filled in sigma antibonding molecular orbital. Next two electrons will be filled in sigma 2s bonding molecular orbital. Next two electrons will be filled in sigma antibonding 2s molecular orbital. Next two electrons will be filled in sigma 2px molecular orbital. Next two electrons will be filled in sigma 2px molecular orbital. Now pi 2py and pi 2pz, they both have equal energy. So electrons will be filled according to Hund's rule of maximum multiplicity. That means first of all you have to fill one electron in each, then you can pair them up. In this way, two electrons will be filled in each 2py and 2pz bonding molecular orbit. Now calculate how many electrons we have filled so far. 2 plus 2 4 plus 2 6 plus 8 plus 2 10 and 4 14. So we have filled so far 14 electrons. Now remaining 2 electrons will be filled in pi antibonding molecular orbitals. Again you have to follow Hund's rule of maximum multiplicity. So one electron will be filled in pi 2py antibonding molecular orbital and one electron will be filled in pi 2pz antibonding molecular orbital. So in this way we have filled all 16 electrons in these molecular orbitals. Now write the electronic configuration of O2 molecule. So we will get sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2px2, pi 2py2 equal to pi 2pz2 as they both have similar energy. Pi star 2py1 equal to pi star 2pz1 because we have filled one electron in each antibonding molecular orbit. Now calculate the bond order for O2 molecule. First of all, you have to calculate the electrons present in bonding molecular orbital. So 2 electrons in sigma 1s, 2 electrons in sigma 2s, 2 electrons in sigma 2px, 2 electrons in pi 2py and 2 electrons in pi 2pz. So how many electrons in bonding molecular orbital? 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10 electrons in bonding molecular orbital. And 2 plus 2 4 plus 1 5 plus 1 6 electrons in antibonding molecular orbital divided by 2. So you will get 4 by 2. That means bond order you will get 2. Bond order is positive. That means this molecule is stable. Bond order 2 means there is double bond between two oxygen atoms. Now come to the magnetic property. So as there are two unpaired electrons, O2 molecule is paramagnetic in nature. And this property of O2 molecule is explained by the molecular orbital theory. I hope now you understand molecular orbital theory. And here I have summarized the energy order for lighter and heavier elements. And this is the only difference between both of them.